Welcome to the last talk in this afternoon session here in this room. With me on stage here are Maximilian and Markus. They are doing quite some hot stuff with Ethernet, EVPN, and automation. This time Max is not doing any EVPN. This is cool. Then it's even more interesting. So please give a warm applause for Max and Markus.
Thank you. Luckily, we don't have to deal with EVPN directly. So, welcome to the internet, to this talk. We know we are between you and the social. We will make this interesting. Pinky swear. Also, shout out to Thomas in the other room. So, I've heard this was quite the choice where to go, and some folks are still coming in. Today, we'll be talking about forwarding and also dropping packets at scale, which we will do for the cloud and present what we have built over the last years. So it's a short advertisement block, sorry for that. Who are we? We are the cloud part of Hetzner. Hetzner has a lot of other things, but we focus on the cloud side of things today. Obviously, we have cloud servers, which need some kind of networking because you want to reach them over the internet. You may want to put a firewall on, in front of them, a stateful firewall, and maybe you want to put them together by private networks. I guess it's called VPC and other vendors, so obviously we also have that. Some load balancers, which may offer, well, load balancing obviously for multiple of your servers. And the interesting part on that is all of the network stuff is not happening in the physical side of the network. That's quite dumb, and we want it that way. But everything we do and offer as features is happening on the cloud hosts, so keep that in mind. Besides all that, we have the usual stuff like some block storage, recently edition S3, and DNS, which today was G8 in the console, so new fancy interface, and much more. Who are we? As Jan said, I'm Max, this is Markus. We are part of the SDN team, which has been founded in 2022, with Markus and Tobias being the founding members and also founding fathers of everything we'll see today. Nicholas and myself have joined later on, so we are 4 folks who are building everything. And in general, at Hetzner, we love to build custom solutions for ourselves, which we also have done here. What are the goals? Well, we are engineers, so we like resilience. Everything should be performant, so you as customers are happy with us. We as operators want to be able to observe everything we build. So in case there would be an issue, we can see what's happening. And if we have tickets, we can figure out what's wrong. Also, we want to be able to extend this and offer cool new features. For example, IPv6 and private networks to prefetch a question would have been come later. And that's why we think dual stack everything, it's 2025. Sadly, the existing stack we currently have, which is based on open vSwitch, so open source software which is readily available, works. It's still in use for over 1 million cloud servers in our 6 locations, but it does not satisfy us very much. And we don't see a future in that. So when the team was forged 3 years ago, the initial task or the initial quest was, hey, what will we do with our stack? Where do we want to go with it? And the decision was, after looking into some technologies like DPDK, VPP, etc., hey, we built something on our own. Let's go with eBPF and XDP. And Markus is going to take it from here and tell you all about the funny details we've got.
Thank you. What we can see on the right is What we can see on the right is the logo of our stack which we built. Does the microphone work? Okay. So we built our networking stack, and we used eBPF and XDP for that. But first, let's begin with what this is. Let's begin with what eBPF is. eBPF is technology which we use to extend the Linux network, the Linux kernel, and it allows us. Yes? Ah, okay, that sounds better. Okay, so what is eBPF and XDP? Let's start with eBPF first. eBPF is a technology which allows us to extend the Linux kernel at runtime using eBPF programs. eBPF programs are made of eBPF instructions as a custom instruction set, and we compile to this instruction set using C code. It's a limited version variant of C, and we can use CLang to compile to eBPF instructions, and then we can use this instruction set loaded into the kernel, and the kernel will verify if this program, this eBPF program, is safe to execute. And if it is, then the kernel will load it into the kernel, and then we can attach it to specific attach points within the Linux kernel. There are many different attach points. One particularly interesting for us is the XDP attach point. But first, let's start with what we see on this page. I think many of you will probably know this picture. It shows the Linux networking stack, the netfilter stack, and the packet flow within it. But I'm not sure if you also all noticed the very first part of it. You can see the box which we enlarged on the bottom. There's a box, the very first stage of this packet flow is XDP eBPF. And there you can see an arrow which skips all of that and transmits the packet to another interface. So we can bypass all of that using XDP. Here we have a picture which shows a little bit better how XDP works in detail and how we use it. So as we have seen, the user space program can load an XDP eBPF program into the Linux kernel and can attach it to an XDP hook. These XDP hooks live within the networking drivers. So we can load an XDP program within the networking driver of our external NIC, and every packet which this NIC receives will be processed by this XDP program. This program will receive a whole packet, just the plain bytes of a packet. It can access it in any way, it can modify it in any way, and it can decide what should happen with the packet in the end after we are done with mainly with it. One thing we can do is just return XDPTX to return it the same way it came in, so send it out the same way it came in. We can redirect it to another interface, and that's the really interesting part which we use a lot, because this allows us to bypass the whole Linux networking stack and redirect the packet from one networking driver to another one. Also, what we can do, we can pass the packet to the Linux networking stack. This way, the data processing will just continue in a normal way, as if the XDP program never happened. Or we can drop it and make it go away forever. At the bottom right, we can see an example for how this would look in a very, very simple C code. It's just a very simple C program which you can compile, which will drop every packet coming in. Not very useful, but you can do way more with it. Of course, we also need state, and for that, eBPF maps exist. This is like tables inside the Linux kernel, and these tables, eBPF maps, can be accessed from the user space as well as the kernel space. Which XDP gives us a lot of flexibility. This means we can pass packets anyway, can implement the networking stack, hcnet, which we called it, in any way we want, and we have a lot of flexibility. But of course, with great power comes great responsibility. This also means we have to pass packets ourselves and had to implement a lot of protocols. So here you can see an overview of some protocols we had to implement. Of course, we did not fully implement them as they are implemented inside the Linux networking stack. We don't want to reinvent the Linux networking stack. We want to build a very specialized one which is exactly optimized for our use cases. So the implementation of these protocols are not fully featured. They are very focused onto what we needed to make the use cases we have, bringing VMs online in the internet, work. So here you can see a very, very simplified example of how one of our cloud nodes works. These cloud nodes, as Max already mentioned, are the instances which run our VMs. So on the left, we can see the uplink interface, or in reality, it's multiple. Of course, we have the regular Linux networking stack running on these nodes. It's also highly used to bring the node up, connected to the internet. It does all the ARP, NDP, BGP stuff. Of course, we also use the TCP stack of the Linux kernel for control plane stuff, storage, and so on. But what we do not use of the Linux kernel is the routing, and which we use to connect VMs to the internet. This is what we have done fully in XDP. So you can see a lot more boxes here. These are the XDP programs. And the first box at the right after the VM interfaces is an XDP program which does everything the VM needs to be happy. So it responds to ARP, NDP packets, it sends replies out for them. Of course, it also replies to echo requests. Otherwise, a lot of people would be very mad, I think, I hope. It also has pod security, and if everything looks right, and we have decided that the packet should go out, when it passes our stateful firewall, which we also built in XDP, I will come to that in a minute. And it will come to a public network gateway program we have, or in case of private network interfaces, we also have a private network variant of it. And this is where we do the routing in our own C code. And we use eBPF maps to store the routes and look up routes and decide where the packet should go. And in case, I mentioned already, we have private networks. These are based on VXLAN, so we also implemented our own VXLAN encapsulation in XDP as well. What the VM also needs is DHCP, because often they don't know their IP address, it's not statically configured. They ask for it, and we tell it which it is. We could have implemented a DHCP server fully in user space and somehow pass packets to it from the VM, but then we would have to securely tell the user space DHCP server from which VM the DHCP request came. Of course, it would have been possible, but we figured it's even easier to just respond to the DHCP request inside the Linux kernel in eBPF. So we implemented our own DHCP server. It sounds a little bit more ambitious than it is, because we don't have to do any dynamic leases. We know which VM will get which IP. We don't have to remember leases. And in the end, what we are doing, we are receiving a DHCP request, transforming it into a DHCP response, and send the packet back out using the information which we already had about this VM interface. Which we also have is a metadata server. It's an HTTP server running on our nodes, which gives the VM information about its environment, the metadata information. Of course, we did not want to implement a TCP stack on our own. This would be a little bit too much. Instead, we have done the other solution. We are running a HTTP server in the user space, and we found a way to tell the HTTP server from which VM interface a request is coming to securely identify it. As we mentioned, we built our own XDP stateful firewall. First, why did we do that? It sounds a little bit fun. We are bypassing Linux kernel. This also means we are bypassing Netkit. This means that we have to implement our own firewall, but this also means that we can implement our own firewall, and we can specialize it to do exactly what we need. And that's what we did. So when a customer defines a firewall in our cloud console, first we validate it, of course, and then we normalize it so we can detect changes. When the firewall didn't change, we don't have to do anything about it with it. When it changed, then we built a graph out of this customer rule set, and every node in this graph describes something about matching a packet. And this graph can then be used to logically optimize it. And after we optimize it, then we can compile this graph into an eBPF instruction set. These eBPF instructions, which we are again generating using Go code, are then inserted into an eBPF template program. Because what we also need to do in a firewall is the fragment tracking or connection tracking, and we did not want to do all of that using generated instructions. Instead, we have written a C program using regular C, which contains placeholders for the dynamic rule sets which are coming from the customer. And when we use these compiled templates, insert the instructions which are dynamic into them, and then we have a finished firewall program. And this firewall program is then loaded into the Linux kernel, And this happens per VM interface, so it's completely isolated. What is also completely isolated is the fragmentation tracking and connection tracking tables. This is a really interesting feature, especially compared to the regular NetFilter stack, and also makes some things easier and helps us to fully isolate customers. Here we can see an example of how this will look like in the end. Here you can see the compiled eBPF instructions, which we generate using our own Go code, which match a packet. Here it's a very simple customer rule set which just allows all ICMP and SSH from a specific IP prefix for IPv4 and IPv6. And this is the instructions which are coming out of this program and will end up in the Linux kernel. The Linux kernel will zip them and execute them for every packet. Of course, we also need our own diagnostic tooling because the Linux tooling does not work for us. We have built a lot of command line tools using Go. I've just featured a few interesting of them here. The very first command is hcnet describe ifaces. It shows us all the interfaces which are currently defined on our C node, our cloud node. The second command, hcnet data plane stats, allows us to view statistics about the packet processing happening in our data path. We built a lot of counters in our data path, which is used to give us insights into how packets are being processed, when something is going wrong, and so on. So here, just a few examples. For example, you can see when the firewall for a given VM interface dropped a packet, accepted a packet, or a time exceeded came because of a trace route on something. Some counters will be increased, but we have way more counters than fit on this page, and we also export them out to perimeters. This gives us really deep insights into what is happening in our cloud and why something is happening. And also we have a command to print our contract table. It's similar to the utility tooling with the Linux kernel, but it's for our own eBPF maps and prints all the connections which are currently active for this given VM we queried the table for. One more diagnostic tool we wanted is the ability to capture packets. Normally you do this using TCP dump, of course, but this does not work for us. In fact, if we would use TCP dump to capture packets on a VM interface, we would not see a single packet. Because we do skip the Linux kernel, and the TCP dump hook within the Linux kernel will not even be reached. To resolve this, we built our own hcnet capture tool. And to explain how this works, I first will explain what you can see on the slide. On the left and the right, we have interfaces, the uplink interface, and, for example, one public interface of one VM. And we have eBPF programs attached to these interfaces, XDP programs. And these do the packet matching and processing. And as you can see, we are multiple programs, and our data plane is built modular. We call one program from the other one using eBPF tail calls, and we have a jump table which describes how these packets are chained together. The really cool thing about this is also allows us seamless updates, so we can update our data plane seamlessly without losing a single packet, which is also a really handy feature of that. The colorful boxes on the top and the bottom, these are the final XDP programs. These are programs which just return the final XDP action, like drop it, pass it, redirect it. Now, what we have implemented is that we can hook into every single one of these arrows. So every one of these arrows is called in our term transition, and we can hook into that to see all packets going through it. This way, we can just use hcnet capture, specify at which transition we want to see the packets, and we can also specify a TCP dump filter, which we compile into our hook program, which specifies which packets we want to see. And we can also write it into a pcap file or filter by interface and so on. And this is a really, really useful tool. One more. No, you.
Well, as Markus said, we are directly hooking into the drivers of the network cards, so the physical ones and the virtual ones, meaning also the TAN driver for the interfaces falling out of the QML process. It's obviously running on Linux machines. And, well, there are always challenges. As this is fairly new compared to the whole history of the Linux stack, also the XDP support in the drivers is fairly new, and, well, if you go on paths which are not beaten out, then you find surprises. The nice example is a bug we found in the Intel driver. I think it was IXBE. And within 24 hours, a maintainer on the mailing list said, hey, I reproduced this in my lab. I see this is a bug. I'll fix it. And 1 to 2 weeks later, it was fixed, and everyone lived happily ever after. However, there are other vendors where we are in back and forth for 2.5 years now. I will not name them, but you may guess. So there are dragons. Another thing is offloads. Currently, we support offloads as the Open vSwitch network stack supports them. So all the, as I said, over 1 million custom VMs happily use offloads to send packets like GSO and stuff. And we don't want to shut them down to migrate them to the new network stack. I guess you as a customer would appreciate that. So the goal is to also implement offloads in XDP, which is bit bleeding edge, and it's a feature which does not exist yet. Also, it's not possible to signal the offloads to the network driver, which will emit the packet in the end. That's basically the missing link and some stuff in the TUN driver. However, as I said initially, we like to build shit ourselves, excuse my French, and so we tried, or more precisely, Marcus tried to add some features and also looked into the metadata support to signal the wish for offloads. So we are also actively developing on the Linux kernel side of things and try to upstream as much of that as possible. In that realm of the metadata support, other big players also using XDP have some proposals on the road, but it seems that there is no one way to go. So maybe we'll build something internally and match that when it comes up in the vanilla kernel. You might be wondering what this funny server is you're looking at. For validation and development, we have one server which hosts all our network cards we have in the fleet, which I believe are 6. And this one also got some fame on LinkedIn recently. So this is one of 2 test servers we have to test all those programs. And all the NICs are just connected back to back to shove some packets through. Bandwidth is not an issue, but we want to see that the box does not explode, which may or may not have happened in the past. Also to test the TUN driver and all those nice things, and to not have to have a virtual machine to test this, we, or mostly Marcus, built the virt.io Go library, which we have also open sourced recently. So we have some foundation to go on. With that, we have a new network stack. It's also running in the internal cloud and also hosting applications which are publicly usable right now. So you may have interacted with this new network stack. It's not rolled out globally yet. We are working on that. Most likely the first place where this will go are the load balancer nodes, which also use the Open vSwitch stack currently. This may require using the TCX entry point. So if we remember the NetFilter graph or the Linux network stack graph a bit later in the process, but fairly early too, that gives us offloads and then we can go from there. But the end goal would be that we have the whole picture and have feature parity to the whole stack. If there is a public beta, we'll let you know. That's all from us for today. Thank you.
Thank you, Marcus and Max. I think we have some time left for some questions. Let me start with a question from my side. I'm just wondering, if you're doing this development work on the networking start, how often did you lock yourself out and had to use out-of-band access?
It happened a few times. Especially we also experimented with other technologies like DPDK and something. Where it happened with this technology, it happened even more often. But of course, we have other ways to access the node, and we have testing nodes for exactly this use case.
Okay, thanks. Question.
Gerd Döring, hi. Cool stuff. I'm curious about one thing you did not mention between the public internet gateway and the rest of the internet. How do the packets find back to your node? Is there some sort of BGP or something?
That's just an IP fabric. As I said, the physical network is as dumb as they get. So it's an IP fabric where all the cloud nodes are connected, and we do BGP from the host to announce the IP addresses of the servers.
So the host has one BGP session for all the VMs running on it, and then the XDP packet just grabs the right IP address for itself.
Yes, the stack, as Markus has said, we use some eBPF maps, so we have a FIP in the stack. So the eBPF map is basically the line card, if you will. And so it knows what to grab and where to send it, and everything we don't know we pass to the host.
Cool stuff.
Holger Zuliger speaking from Heron. Yes, nice work. And it seems that this is the 5th or so firewall implementation for Linux. But my question is, how often can you update an eBPF program, and what happens in between this update with the forwarding traffic?
This is a really cool feature about the tail calls which we use to chain these programs. The tail calls use an eBPF map to look up which program is coming next, and changing the program address within this map is atomic. So one packet can just arrive in one program, and then the next packet will arrive in the updated program. Updating the program is not very expensive. Of course, we have to render a new program using Go, and we have to load into the kernel, and the kernel has to verify that it's safe to execute, but the overhead is not that big that it's an issue. And if it was, we would have limit it.
Any more questions from the audience?
And to add to that, yes, it is the nth implementation. However, as I love NetFilter, it has one central contract table and a lot of shared state. So if you have n virtual servers on the same host and one of the customers is naughty, that might happen, then we do not want this machine to interfere with others. So in our design, it's completely coupled, as Markus said, own contract table, on fragment table. So there is no interference between systems.
One important thing to note is if we wanted to build a fully generic purpose network stack, we would have just used the Linux kernel because it's a really great general purpose network stack. But what we wanted is a stack which is completely specialized to what we needed, and exactly this feature set, and this is why it sometimes makes sense to build things on our own.
Hi, Marcel Menzel from DKIX. I have just interested in, did you have any look at BP filter when implementing your firewall on the XDP? Or did you just like take a look at the existing BP filter code, or did you just like implement everything at your own from scratch?
We implement it on our own, but the general idea is quite similar. So in the end, we are compiling a rule set and matching it. How you do that will probably differ a lot, but the end result is quite similar, I think.
Any more questions from the audience? No? Then let's give a warm applause for this awesome talk to Max and Marcel.